Okay, so let's start. So welcome everybody to our PhD in Computing Colloquium series. So we're going to have it each semester, and this semester we have 3 talks, at least we scheduled. And the first talk is going to be by Dr. Dirk Beyer, benchmarking and preserving tools for formal methods. And he's going to show the slide of how he's going to he's traveling back and forth for his work. So right now, Dr. Beyer is a full professor of computer science and a research chair of software and computational system engineering and LMU Munich. It's Ludwig Maximilian University in Munich, Germany. And before that, he was a full professor of computer science at the University of Passau. Also in Germany, he was assistant and associate professor at Simon Fraser University and British Columbia in Canada. In Vancouver, and postdoctoral researcher at EPFL and Lausanne, Switzerland, in the group of Tom Hedzingers. So Dr. Beyer holds a master's degree and a Ph.D. degree in computer science from Brandenburg University of Technology and Cottbus, Germany. In 1998, he was a software engineer with Siemens. In Dresden, Germany. His research focuses on models, algorithms, and tools for construction and analysis of reliable software system. He's an architect, designer, and implementer of several successful tools. For example, CrocoPad is the first efficient interpreter for relational programming. Also, he developed SSVisu, is a successful tool for visual clustering, and CPI Checker and Blast, which are pretty awesome model checkers. So with that, we can start to talk.
Thank you very much for the invitation to give this talk here. And it's really a pleasure to see so many of you. So I would like to give you some insights from benchmarking. And I work in the area of formal methods. In particular, I do software verification. And this requires, it's an undecidable problem in theory. So what we can do to obtain efficient analysis is heuristics. And the heuristics you can do only if you do experiments, right? So you cannot do the algorithm analysis and prove that this is efficient, but you have to try out with experiments. And it's actually a lot of experience. And this caused first us to develop a tool that supports benchmarking and to also analyze what are the problems in benchmarking. And this is the first part of my presentation. And the second part of my presentation is about how to actually make these tools available on how to make them work in different environments. Please, if you have questions, please interrupt me. I can shorten my talk later on. So if you have questions, please tell me and we can do an online discussion. So everything I say in the first part is actually written in this paper, Reliable Benchmark Requirements and Solutions, that was joint work with Stefan Löwe and Philipp Wendler a couple of years ago. So we published this in the journal STTT. First I want to motivate. Do you mind if I close the door?
No, so good. So they will, whoever's late, they will have to open the door. Can I close the door?
It's loud. So we would like to motivate the need for benchmarking. And I want to give as an example a competition. SVComp 25. These are those numbers are from this competition on software verification. It's one of the largest, actually the largest competition in the area of formal methods. And so what was benchmarked? 62 verifiers, 18 witness validators, and there are 33,000 verification tasks that they have to solve. And just to give you an idea, almost 1 million runs of verification tools was done in that competition. So this took over 2,000 days of CPU time. Of course, we didn't wait so many years, but we had lots of computers to distribute the computation.
What's the size of the code base? So that you have that many runs against what size? of verification?
They range between 10 lines of code and 150,000 lines of code.
Okay.
And each of the verification results in the competition is also validated. So validators are programs that work like verifiers, but they get as input also a witness that the verifier created. And they justify that the verification result is correct. And we had almost 22 million of such verification validation runs, right? So this is a huge amount, and this nobody can handle. So we need tools for that. And this is why we need benchmarking tools. Another motivation from my own group, we are developing one of these verification tools, namely CPA checker. And we do regression tests, of course, as every software engineer should do. We have 15 different tool configurations that we run, each on about 4,000 verification tasks. And so in total, in the last 8 years, we ran 150 million such runs, right? And so we use BenchExec. That's a tool that I will talk a little bit more in part one. And BenchCloud is a infrastructure to distribute verification workload to many computers. And so together with regression testing and research and teaching experiments for CPA checker, we do about 1 million runs per week, right? So it's a lot of stuff that's going on, and that is all done automatically. And we need to make sure, for example, that the processes are terminated reliably, and that we measure the time reliably, so that we can compare whether there are deviations with our performance. Okay, so now let's go to the stuff that we need to address. So just to give a context a little bit. So we are doing research and formal methods, and there are different ways to evaluate research results, right? And for example, if your result of the research is a theorem, you have to provide proof, right? We are not doing that. If your result is an algorithm, then you probably do algorithm analysis, and you do proof properties like this is big O of n square or something like that, and you prove that. And our algorithms are not terminating sometimes, right? So we do heuristics, and this is what we do. So we do heuristics for complex problems, verification, and what we need to do is performance experiments. So we try out an algorithm and have to see if our ideas are good or bad, right? Sometimes we have bad ideas, and then the performance is not good. So that's what we do. And evaluation of performance is where we have to execute the tools and do repeatedly empirical work there. So if you look at papers, often you see a comparative evaluation. So authors are developing an algorithm, and they take some other tools to compare. What's the problem with that?
They pick good tools.
Huh?
What if they didn't pick good tools to compare against?
They pick the tools, and even that they pick the parameters that they give the tools, right? But they should actually ask the authors of those tools to tell them the best parameters. But nobody can do this, right? Would be much too work. Yeah.
It's also the problem with doing that is they could be lying.
Yes.
They could just be lying out their ass.
Right. Then in the last decades, there was a new way to do comparative evaluation, namely competitions. So there are tool competitions where the authors of tools enter the tools into the competition, and then some organizer presses the button. And the developers of the tool announces here, please use these parameters, right? And then you have really an independent comparison of the results. Also for this, you need a lot of benchmarking. So in terms of reproducibility, I would like to bring up the notions because they are important of repeatability, reproducibility, and replicability. You might know these from, if you have ACM papers, you get badges. If you have experiments, right, you can have an artifact, you have the artifact available batch. If the artifact is evaluated, then they tell you whether it's good or not. So you can get an artifact evaluated batch. And there's also a batch for reproducibility. If somebody reproduced the results, then you can get a batch for that, and also for replication. So what is replicability? So everything needs to be documented for that, right? Repeatability means you can repeat. So it's not that by chance you ran the tool and it was spitting out this interesting, nice result, right? And you can report this, but you cannot do it again. Repeatability means you can systematically do it again and again. So it requires also that the tool is deterministic, and it requires reliable benchmarking and infrastructure that does the execution, right? And this is what we want to cover here in this talk. For reproducibility, you need a little bit more, everything above, but also that the tools are available. So a different team, reproducibility means a different team can take the tool and execute it and achieve the same results or similar results. So the tool must be available, the benchmark set must be available so that the tool can be executed, and also the environment, like which packages have to be installed on what version of the operating system. And then everything must be published and archived, and also, of course, appropriated licensed. If there is something available that does not have a license, you cannot use it, right? Because you don't know if you're allowed to. So we need licenses also. And replicability is not discussed here. This means that there is something described in a paper and somebody else implements it, right? Replicates the experiments. So this is a little bit of the context. And now about benchmarking. Benchmarking is very important. I made the point already that you want to evaluate tools and competitions also. You have new ideas, you want to implement approaches and evaluate them. And also, as I showed, if there's tool development, tool developers have to test and performance measure their tool all the time. So we need reliable, reproducible, and accurate results for that. So benchmarking is very hard, and there are many aspects of it. For example, influence of input-output, network, distribution of tools, use different distributed on several computers, user input, right? This makes it very difficult. But luckily, for solvers and formal methods, this does not apply. This is not relevant. The input-output, there's just an input file with the problem, and the solver has to work on it. Networking is switched off. The solver has to do it on itself, on its own. There is no distribution and there's no user involved. Right? Who knows SMT solving? Not so many. Okay, so you have a logic formula, and you can write the logic formula in a language that is understood by tools. Those tools are called SMT solvers. You give it, and it tells you SAT or unsat, and that's it. Right? There's no user interaction. But is it easy just because we don't have these four problems? No. The problems that we really have is we have different hardware. We have new processors that have really sophisticated architecture. There are cores of different speed. There is distributed memory, this NUMA, where you have several CPUs sometimes in a computer, several memory banks in a computer, and this all communicates, and you have to control this. Heterogeneity of tools. So tools are starting maybe with a Python script and then executing some binaries and then getting back and start some solvers, and this back and forth all happens in these tools. And also we want to execute benchmark jobs in parallel. So we have large machines that are able to execute several of these runs in parallel. But then how do we make sure that they are not influencing each other? So this is all relevant, and we have to address this. So our goal is we want to help to make performance benchmarks reproducible. We want to avoid non-deterministic effects from the environment, from the machine, and interferences with other runs. So we want to provide a defined set of resources. Accurate results we need, and this is for verification tools and similar. So this infrastructure that I will talk about is also used for SAT solving, for SMT solving and stuff like that. And the only operating system on which we can do this is Linux. So all I'm saying is about Linux. Okay. Now, here's a checklist of what we need to take care when performing benchmarks. We have to measure and also limit resources. So of course we want to measure time, right? Because we want to know how efficient our algorithms are. And we want to measure their memory consumption. But it is also important to limit these resources. Why? So we want to execute thousands of different runs, right? So we cannot afford that one is not terminating, right? So we must enforce a timeout at a certain point in time. For example, we can specify, we give every execution an hour or 15 minutes or 5 minutes or something. But we have to specify something because we want a predefined termination of the experiment if it does not succeed. And also with memory, right? We have every machine has a certain amount of memory. For example, 15 gigabyte or whatever, 30 gigabyte. And then if we want to measure and control the performance of a tool, we have to give it less, right? Because the operating system takes about 500 megabyte or a gigabyte, and then there's also caching of the disks and so on. So the operating system does a lot of smart things that also needs memory. So we cannot give the whole memory of the machine to our experiment. We have to limit it to something smaller of it. So for example, if the machine has 16 gigabyte, we can give 15 to the tool at most, right? This we have to, therefore we need limits. We need to terminate processes reliably. As I mentioned already, we cannot wait indefinitely. And once we want to kill a job, we really must ensure that there is no remainders of this. So all the sub-processes have to be terminated also. Assign cores deliberately, right? For example, we don't want to have one physical core with 2 virtual cores running 2 different jobs because they would share the resources and there would be a very large divergence of the time. Non-uniform memory accesses, NUMA, is very important so that we don't run a tool on this core. If this is the CPU, right, we run it on this core and the memory is here. So all the memory access is routed through other cores or buses on the CPU, slowing down other things on the machine just to access this memory. We have to assign to something that runs on this core memory that's close to it, right? Avoid swapping, of course. If we start swapping, performance is anyway not good. And we have to isolate individual runs. So if you, first of all, we don't want to allow them to use networking or use shared files. And we want not one tool write a file at another tool use that file, right? So these are the things we want to do. And I will go through these a little bit more in detail now.
No, go ahead.
But please ask, right?
Well, if you're going into detail, I can wait.
Okay, let's see. So first, measure and limit resources. So we need to measure wall time and CPU time for sure, right? Then for memory consumption, what can we take there? So traditionally, classically, the operating system provide the size of the address space, but of course, this is way too large, right? This is too much of an over approximate. The size of the heap is too low because we also have stack. We need to measure this also. And size of residence set is also not really accurate. And then what we want to measure is the peak consumption, right? So also sampling does not work because we might miss the heap, the peak of the memory consumption, right? Or we have to do the sampling so frequently that the sampling itself slows down our experiment. Yeah, we always need to define memory limit for reproducibility, as I mentioned already. Otherwise, the memory is limited anyway, But the question is whether we limit it to the same amount or whether we do not limit it, but the operating system limits it to whatever is left after the operating system takes its share. And of course, we need to include sub-processes in the equation. Yes.
So would this work with somebody who, say, rewrites or overwrites mallet? So if we have a custom memory implementation, would the approach that you're taking later on consider that?
You mean the CLIP that the kernel uses is patched
Yes.
with a different memory allocation. So what we later will use is called C groups as a solution.
Okay.
And C groups is a kernel function.
Yeah, we're using that.
And this is used. So I think it will take it into account.
Okay.
But I'm not 100% sure if you can trick the kernel such that you can take memory without it noticing it. But I'm pretty sure it cannot.
Well, we want to keep it under the C group.
Yes.
Yeah.
Mhm. Okay, let's talk about CPU time, for example. It's very easy to type time, the command time, and then the verifier, right? And then you think the verifier is executed, and then it reports the real-time user time system time, right? This is what many people know and are used to use. But this is very inaccurate because the verifier could spawn sub-processes, right? And the sub-process might, for example, not terminate. For example, if our verifier terminates and this one not, right, then this time of this sub-process is not included because the system call is using the wait, and waits basically for the termination signal of the sub-processes. And then with this signal, it is accumulating the CPU time. If this wait is not coming, then it's not accumulating, right? So you are basically measuring only part of the CPU time. So with C groups, this is all included. Everything that runs in one C group is included. So this is what might not end up included. Then with memory, suppose, so there is this classic tool named ulimit, and you can give it a size of memory, and then you think the verifier uses only 1 gigabyte. What do you think? How much memory can be used here in this picture? Well, the truth is every process can use 1 gigabyte, right? So that's really a problem. So each of the processes can use. So what can we do, right? And then we are not talking yet about shared memory, because this is, so if we accumulate, right, then we would accumulate too much. So how to terminate processes? So if we send the kill signal to the verifier, then the kill signal is not reliably propagated to all sub-processes. And for example, there could be a sub-process that we want to kill, right? But before we killed it, it just was spawning off another sub-process. Then this we never end up catching all of them, right? So what C groups is doing is it freezes all the processes so nobody can execute anything. Then it gets the process IDs, it kills all of them, right? And only then it could continue computing, but then the C group is empty. Right. So just to enumerate a couple of problems that are really there when doing benchmarking. So hyper-threading, I explained already, and shared caches is also a problem. Like you have several cores, and some of the cores share caches. And if you, for example, say, okay, each of my benchmark runs should get 4 cores, and my machine maybe has 8 cores, then I should use the 4 cores that are close together in the architecture, right? And not just every second one or something like that.
So are you also limiting the dynamic hardware that goes and adjusts the clock speed?
We are usually switching off the what is it called?
Variable performance or whatever.
Turbo boost, right? Yeah. Also, so this is usually switched off so that it is in.
Well, I found even with turbo boost off, there's still quite a bit of variance. But anyway.
Yes, and nowadays there are processors with different speeds of the cores, and you have to make sure that you use cores of the same kind and not at all use the other ones, right? So that you have comparable results. Yes. And so NUMA, we talked already about it. So we use the memory regions have different performance depending on which cores we use. And there is a hierarchical NUMA, which makes it even more complicated. And so here is an example picture. If you use Debian as operating system, there's a package hwlock, which you can install, and then you can type ls-topo, and you get exactly this picture here. And basically, this says that so the whole thing is your system, and the system has several CPU sockets, like the circuits. Right? These are called sockets here. So this, for example, has 4 sockets on it. Right here, we also see, and the sockets each have 2 memory blocks and regions of CPU cores. Right, so you see that this CPU socket here has 1, 2, 3, 4, 5, 6, 7, 8, 16 cores, and you know that if you use if you run a process, you should never use this core and this core and this core and this memory, right? Because then these 2 cores would have inefficient memory, but you should have these 4 cores on this memory. So this needs to be taken care of, right? So this is a major source of divergence in the performance. And then something that anecdote from executing a competition. So people were thinking of cleaning up stuff. Right, they wanted to kill their solver, and they use these commands here, right? But what's the problem?
Children.
Children. So somebody else is, right? Another process is running in parallel on the same machine. That's also trying to solve something with Z3 or minisat, right? And those are also killed. So what we need is isolation, like containerization, that a tool never sees processes that another experiment does. So there's kind of ownership of the resources and the processes. So we have to take care of this also. Then temporary files. So if there's a tool and the tool developers want to store something temporary, they use probably the TMP directory, or they even are smart and read out the TMP variable that specifies where to write temporary variable, right? Which is already nice. But still, if it is named like mytool.tmp, then if a benchmarking runs the same tool on several inputs, right? Then this is overwritten and there is a race there. So this is problematic. Then sometimes you cannot reproduce the result because you cannot reproduce which tool we are running in parallel. So clean up after running. So this also requires isolation of the tools. So now I speak about the solutions. So C groups is the solution. It's a kernel feature of the Linux kernel. It's called control groups, and they track everything about processes, time, memory, I/O, and so on. And this is like a file system. So C groups are a hierarchical tree of the processes. Every user can have processes, and you can have sub-processes, and you can start new groups and so on. But the processes in one group can never escape this group, right? And this allows you to measure the resources, allows you to kill them and stuff like that. So namespaces, the second concept, also provided by the Linux kernel. It's like a lightweight virtualization, and it's changing how the processes are seen by a process itself. So all the identifiers, for example, the process IDs, they are different. There are different numbers assigned. For example, if you have a particular process ID, that's a different process seen by different processes, right? And this we use to build application containers. And this does not require root access, actually, right? So it's not like a Docker where you have to run it as root. And and the third part of it is overlay file system. So I was mentioning the cleanup after an experiment is run, right? So the tool is run, and the tool writes files on the disk, right? How do you know which files it was writing, right? You need to remove them afterwards, right? Because you want to run the next tool on a clean infrastructure. And what you can do is overlay file system. So basically, you hook in a file system on top of another file system, and the tool writes to this file system, right? And then you can delete this file system, and all the files that the tool wrote are gone, right? You can save them if you want, if you need the results afterwards, but you can make sure to get rid of it, right? So here you can have different directory modes, access modes specified. I'll go over this faster. So what we have is benchmarking containers. This encapsulates the group of processes. It limits resources. We can measure the resources. We can control how processes are organized, network, and file system stuff. Right? So we have a container solution that we can use. And the tool is called BenchExec. BenchExec is a framework for reliable benchmarking and resource measurements. It provides an easy-to-use interface to the C groups, namespaces, and overlay file system, because those are not so easy to use. You need to read up a little bit how to use them. And it allocates the hardware resources appropriately. So that is open source. Everybody can use it. It's written in Python. It's used by several competitions in the meanwhile. And it's developed usually for solvers and formal methods, but it's applicable also for other application areas. Here's an architecture overview. So basically you have a benchmark definition. So this specifies which input files you want to give to which tool and what are the parameters to run the tool. And then BenchExec takes the benchmark definition and all these input files, multiplies out, and calls a tool called runExec for each of the benchmark instances you wanted to have, right, with the parameters and with one of each these input files. And then it writes out an XML file. And with this XML file, another component of BenchExec, namely the table generator, can also generate HTML tables and CSV files and stuff like that. Right? So the inner one is called runExec for one single run. BenchExec is for running multiple runs according to a benchmark definition. And the table generator is for post-processing. So that's basically what the tool does, right? I will provide the slides if you want for later use, and I will go a little bit more quickly through these details here. So this specifies, how you specify limits, and also illustrates here, like this is one process. And runExec takes care of the isolation against the others and limits the resources against the machine that you have. And the resources are mainly CPU cores and memory. The BenchExec does the multiple runs, allocates the hardware resources, like it looks at the topology of the machine and assigns to each run so many cores as the benchmark definition has specified, right? And it looks at where is the memory and stuff like that. And the table generator aggregates the results and makes it nicely to show to users. And benchmark configuration is containing all of the data that we need, right? Like parameters, limits, how to set up and so on. Okay, so there's a paper, as I mentioned at the beginning. If you want to read more, I will give the slides and the references if you want. So be careful when benchmarking. There's this checklist. If you have to benchmark, remember, you can look up the checklist and go through if you have done everything correctly. Don't use the old tools that are outdated and are not yielding reproducible results.
Does it force determinism in any way? Does it
It does not force, no.
Okay.
But what we can influence from the benchmarking, it tries as much as possible to have it deterministic. For example, you have non-determinism if you go through other cores to access memory, right? Because then it depends on how busy the other cores are. And this is so basically the experimentation error.
So for limiting I/O, does it go through and mount those into memory then, associated with those CPUs, so that the I/O between the two processes don't hit?
So it tries to find the shortest path.
Okay.
But if the processor or the operating system does not allow, then we cannot do anything, right?
Okay.
So for example, if you don't have the hierarchy, then we cannot do much. The topology, and we use tools like LSTopo to find out, and that's actually all written in the /proc directory, how the system looks like. And so you have to dig through there and find out how the machine is working. And that is all BenchExec is doing it, right? And calculating the best possible way. So now a little bit about the part 2. So I want to talk about two endeavors. One is called FM Tools and one is called FM Back. And so the vision is 3 things. We want to have formal methods work together to solve hard problems. We want to integrate solvers with each other. And we want to have that SMT solvers and testers, they all use common interfaces for interaction. Right? So this is the vision that, of course, it's not achievable in the short term, but maybe in the far future. But now, what can we do in the short run? So let's look at find and reuse and conserve, these 3 things. So which tools for software verification exists? Let me ask you an easier question. How many tools for software verification of C programs exist? Who thinks it's 10? 10 or below? No? So everybody thinks it's more. So who thinks it's 50? 50 tools for software verification. So you think it's more than 50 tools for software verification of C programs?
Are we counting general purpose verification tools or special purpose bug fighting tools?
So like for assertion failing, right? Okay, so I can give you the answer. It's 62, right? There are 62 publicly available tools that participated in the last competition. So it's a lower bound. So there are more of them, but we know 62 are available. Everybody can download and tool them and use them. Right? So then how would you execute them? Right? What do you think if I tell you you have to use the tool CBMC to verify a C file, right? What do you imagine? How long? Like if I say start now, do you need 10 minutes, half an hour, 1 hour,
A week.
a week? So the goal is to have this instant, right? So that you have a C file and you can instantly run it. So how to find documentation is the first problem, right? Every tool developer documents it in a different way, and how to find the papers that are written about CBMC.
So you're talking about research tools.
Yes, research tools. And commercial tools,
Commercial
even
is
worse,
it
right?
the worst?
Because they have so much documentation.
Okay.
And so how to find the shortest how to get started, right? And conserve, of course. I want to execute it. What operating system, what libraries do I have to use? And my solution shall support documentation, should be easy to query, support long-term availability, must come with tool support, and it must be compatible with competitions. So here's a solution that I wanted to propose. It's a GitLab repository, and there is a folder with YAML files. YAML is a file format that almost everybody knows. It's just you write text colon and some values, right? And you can structure this and have hierarchy and so on. So what it contains is the location of the tool, the license, whom to contact in case of questions, a project website, options to give to the tools, requirements, and resource limits. And those should be maintained by the community, by the developers, and by others. And now I want to show you an example. Of course, I take my own tool here to do advertisement for it, but the tool. So let us look at one file in this library, right? This is called cpachecker.yaml, right? And it has this contents. So it has an ID, it has a name, how the developers want it to be written, a little description, what input languages it supports, where to find more information, where to find the source code, what is the license of the tool, right? What is the, okay, this is a technical detail here, what format of this file actually is used, and then who are the people who can change this entry, right? And so this is about the tool meta information. Then we have maintainers. So every tool has maintainers. For example, here it was given with an ORCID, so that is uniquely identified where they work and how to reach them. And there is also versions. What versions do the developers announce to be used? For example, this one has following versions, version 4 and version 4 hyphen validation. And it is available at the DOI, right? So it's long-term available. The options that the developers tell to be used, how to execute it. So you need the Ubuntu package OpenJDK 17. You can also use this container here to run it as a base container image and so on, right? So you specify actually how to get the tool. And here's literature. So the developers announce these papers that you should read if you want to learn more about the tool. And that's it, basically. From those data, you can easily compile other, display the information differently. So, for example, this is a web page that is generated. And here you see a more nicely formatted version of the information that I just told you. And so there is this initiative called FAIR. FAIR means it should be findable, accessible, interoperable, and reusable. And this way of the repository, how it works, is actually fulfilling this, right? It is using a machine-readable language. It is using DOIs and ORCIDs and all that stuff. And there is, so how to ensure the environment? We have implemented a tool that is called FMVec, which is complementing the data FM tools, right?
That's smart. No, I like how you've done it.
Okay.
To verify that it actually works.
So basically, this is a tool that you can give the command run, then the tool name, and now this string basically it's looking into this data repository for a file named cpachecker.yaml, right? And it finds the DOI where to get the tool, downloads the tool, executes it with the parameters that the developer specify. And by the way, if you don't want to use the latest version, you can specify the version here. And then it, digs what I showed you before. It digs under the version, which DOI it is, and what options to use, and so on. And then you have your actual parameters, and it runs it in a Docker container with everything installed that the tool needs, right? So here's how it works. So FMVec uses a copy of the FM tools, these YAML files, and it provides several features. It has cache, it has config, and so on. And so here are different command lines that you can not only run, but also run in a manual mode and also run in a shell mode. But I want to skip this for now. But yes.
So one problem that I've experienced before is that sometimes one of these formal methods tools depends on a old version of a tool that sometimes has bugs on one architecture. For example, I think it's Z3. One of the releases of it doesn't work correctly on Linux only on ARM64. And if I'm on a Mac with an ARM64 processor and I try to use a tool that depends on it,
Yes.
then if I does this support Mac, and if so, does it also support emulation so that it can automatically use something like Camu to emulate AMD 64? Or can you speak to that?
So to be 100% sure, you should use a virtual machine with the operating system that the tool people recommend. And then inside that, you should use the Docker container that has everything installed what they need, right? So in this here, right? So basically the tool, so for each version, they can specify a different container, right? And inside that container, which packages have to be installed. So you can reproduce the containers that they guarantee to be usable. And they would need to make sure that they have the right Z3 version in it. So they should ship, right? If they depend on a certain version of Z3, then they have to ship it in their container to make it reproducible. So time is over. Conclusion of the part 2, right? So I wanted to speak about the FM tools, a library of tools and information about those tools. There's a knowledge base that can be generated. It's available here. So here you get the human readable version of it. We can conserve tool versions and all their requirements that they come with. Zenodo is very helpful there because we can package a tool, upload it there, get a DOI for it, and it's stored forever, or at least as long as the European CERN Center is alive, right? And we can run the tool in FMVec. If you are interested, I can also give a demo later on. And please take a picture. No, you don't need to do a picture, but I give the slides, right? And we make it available somewhere. So thanks a lot. Here are some references also. And I am here for your questions. Thanks a lot.
That's time for questions. If you have any questions, please raise your hand.
So do you also pin threads to specific cores to prevent? Okay.
Yes, normally we do, and this should be done. So where's my example command line? Here, for example. So basically this run exec command tells we execute this tool command line, and this specifies that this tool is allowed to use only those cores and this memory node 0, right? So this means specifically here we have two memory banks, 0 and 1, and 0 for basically it is close to these cores, and it would not be advisable to use, for example, core 8 and 9 with this memory node. For if you use core 8 to 15 and the other ones, then you should use the memory node 1. So you need to pin the process to run on a certain number of cores.
But within that number of cores, it can run on any one of those?
Yes.
Okay.
And usually we also how to say, we can specify they should use only 2 cores, only 1 core. But at the same time, if you want to do really accurate, 100% accurate results, then you basically can say that I reserve 8 cores. Suppose you have a machine, you have a CPU with 8 cores, right? So you can tell BenchExec to reserve 8 cores, but the tool is allowed only to run on core 0. So this means all the other ones are forced to be idle, and nobody else can run anything on that, right? Because they are reserved. So we have a one, on the one hand, we have a limit. On the other hand, we have a requirement. The requirement is 8 cores. The limit is 1 core, right? So, and you can configure what, so for example, in the competition, software verification competition, we have almost 200 machines with each one CPU with 8 cores. And we give everyone 4 cores. So we have at most 2 different executions on one machine. Right, and if you, so this is basically, we did experiments to have enough, how to say, tolerance, the tolerance as low as we want. If you want to have a lower tolerance, then you basically have to say, I want to have some cores idle or something like that.
Do you have any recommendations for using BenchExec, like with a workload manager on a cluster? Like on a cluster, if you're using a workload manager, do you have any?
So we use a tool called Bench Cloud for our cluster. So the available solutions like Slurm, for example, they do not provide the C group features for measuring and limiting. So you would have to implement something there. And our so-called Bench Cloud is a job distribution platform that runs. So it distributes, it deploys the runs on different machines, and on every machine we have the run exec running with the parameters specified, right? So basically there is a manager that gets the benchmark definition and assembles all these command lines and looks at what machines are available and what is specified in the benchmark definition. And then it calculates which worker gets how many processes at the time and with which run exec command. This is how it works.
So then how do you account for network latency? Sometimes you have to account for network latency sometimes.
Sorry, say it again.
You have to account for network latencies when benchmarking clouds.
With latencies.
Network latency.
They turn off all network processes, so you can't
Asking
reach
about
network.
latency.
Okay. Yes, we switch it off. The tools that we benchmark cannot use networks. So the approach that I was talking about is not appropriate if networking is involved, right? So networking would involve, for example, even busy waiting or something like this, and then you have non-deterministic run times. And also, if you want to benchmark a solver and you outsource computational tasks to the cloud, then you are not measuring them. So, okay, other questions?
So I have a question. So you had, as you started your talk, you said, oh, we need to take care of this, we need to take care of this. So how many of those were reactive and how many of those were proactive? So you start running competition like, oops, they're now sharing processes or something. So, or how many of them you thought ahead of time?
They are all reactive.
All reactive.
So we started. We started CP Ethical development in 2007, And I started organizing the competition in 2012 for the first time. And at that time, we started writing scripts to run these. We had at the beginning, some scripts to execute those tools, and those were maybe 100 executions or so. And and the scripts were growing. And then we ran into all these troubles, like, for example, this one here, right? It really happened, and we were scratching our heads. Why is it like this? The time and the next time it fails, right? Or something like this. Why it gets the points and next time not. And the same also this one, right? We really had, and you cannot find these. So there is, a tool was so crazy to overwrite the input file. Like they did some pre-processing instrumentation and wrote the file to the original, right, to replace it. And then next time, the next tool did not understand this file. And so we understood, okay, we have to make it read-only. and later on, of course, we had these overlay file systems and so on. So basically every lesson learned we have is, we didn't make them up, we experienced them. We learned the hard way. Yes, unfortunately, but it's system science,
Systems, yeah.
system engineering. Yeah,
Very practical.
yes. And also it's interesting that no other tool existed, right? So the other competitions, they used time and U limit and so on. So venture exec was really a needed thing, and we just developed it to survive with the competition and to be able to run the experiments. So it's really a zoo of different animals that you have never seen before. All these tools.
Well, I wanted to ask, so when people ran kill all the kill specific task that was running, it would kill all of the tasks running that tool. So, yeah, that seems like a accidental mistake there. I can see why you guys built this.
Yes, and now every run is in one container, right? Completely in isolation. It cannot kill. It cannot kill the same solver anywhere else. It cannot kill the same tool anywhere else. It can just not do anything outside its process namespace because it cannot see anything else. Right? This is really why we need why we need isolation. So these killing accidents are not possible anymore.
That's good. So it accidentally shut down some other competitor's task that's using the same solver, for example.
And also, I mean, these container solutions are also made for security reasons, right? So an application should not see too much of the operating system. So all the operating system processes are hidden, right? So you cannot dig around and see. Also in file systems, you cannot dig around what is installed on the system and stuff like that.
Seems like a song, another good reason.
Yeah. Yeah, but that's basically, the solution is very similar to Docker, but Docker also comes with the file system. Basically, it unpacks an overlay file system, and then you have all the packages installed that are in the Docker image, right? So it works in the same way, but we want to have this as lightweight as possible, so that it takes only a couple milliseconds to start it. This one exec itself, right? It should not consume a lot of time because, as you saw at the beginning, we need millions of runs, so we cannot afford a second because this would mean a million seconds.
Second question. So more likely as everywhere else, now verifiers might use AI tools in some aspects. So how are you going to deal with that? Because it would require either networking or
Or an NPU or a graphics card.
Yeah.
So I can say something very undiplomatic, and I can say it's not my own opinion, but it's the opinion that somebody about benchmarking should have. So all the research papers that deal with online AI should not be published. They should be published only if they basically download the
Basically,
LLM,
you need to install the own.
right, like Llama or so. They have
They're not reproducible.
yeah, so you need to have it in a container, right?
Yeah.
So that in 10 years you can reproduce the result because it has not learned in the meanwhile, right? But all the online LLMs, they have
So
learned in the meanwhile.
Still no networking. You're going
Yeah,
to.
no networking, no networking. Yeah. But I don't. I mean, it would be right. The question is, if a paper is published about something about LLMs today, right? Next month, it's not holding anymore.
Next week.
Next week, it's not holding anymore because the LLM is much more
Much
advanced
more,
in the meanwhile, right?
Well, self-transmuting.
So it's really hard. I can understand that why people are using online LLMs, but it's a problem, and we have to solve it as a community. What would be the agreement, right? So we are there now in the software engineering community. We are there to require artifacts to make research results reproducible. So most of the conferences require artifacts, some not. For example, ASE. I don't know. ICSI, actually, our largest conference was last with artifact evaluation. So, but still, this is accepted now. Reproducibility seems to be understood that this is an issue we have to think about. But about the LLMs, it's coming up. Nobody has thought about it, and there are no community standards to adhere to. Open task. Yeah.
Okay, one last question. We ran a little bit late, longer because we started later and we had questions. Last question, going once, going two.
Have you thought about pinning the specific application or other item requirements? Because if you're just pinning the version of the tool, but you aren't pinning, say, the environment, you notice you only have the Docker container, but there's a lot of other things that are associated with that when you pull that in. If it's calling a sub-process that's not part of the tool itself per se, are you pinning those other items?
So by
pinning, I mean
Defining.
defining the package and specifically locking it to a package version.
So the developers can do this. So what we see here is those developers, they require only 17, but not which specific 17, right?
Yeah.
They could, you can specify more like dot something, right?
Okay.
You could do this, but this is not used so far. But we also have a key that is called full container image, where you have installed everything. Like you take this container and you install all the packages that you need, and then you are sure that this is the package. Use this container, and everything is basically pinned there because it's in the container. Yeah. And the next would be basically not give these Docker IO strings, but give the UIs here, and basically download the container, put it on the Nodo, and then if you reproduce, you download the container from the Nodo to make sure you have really that one and execute this container. That's the next thing we want to integrate here. Thank you.
Well, I thank our speaker again.